So we're going to continue with chapter 15 on oscillators, and we had looked at a number of different topologies and configurations, and the one that we're going to take a look at today is probably these days the most pervasive and most widely used and modern, which is based on crystal. So this is crystal. So that's what we're going to look at. So a crystal. So a crystal is a device that works on the principle of a piezoelectric effect. And the symbol for a crystal looks like this. Okay. And the piezoelectric effect is such that when you apply a voltage to this piece of material, it vibrates and it changes its frequency characteristics in terms of how it behaves, whether it behaves inductive, capacitive, and whether it resonates at a fundamental frequency or it overtones. So this piece of material, which usually is quartz, it can also be made out of a very hard ceramic, so something very brittle. So that this can be modeled. This can be modeled as an actual circuit. So this has a model. So from a terminal perspective, so this thing can be modeled. So you can have an L, a C S for series, a CP for parallel, and a resistance. Okay, so that's essentially the model. Now, the other characteristic of this device is the reactance curve. So if we were to plot the reactance versus omega, so this would be the reactance, we would see that it looks like this up to, if this is omega s, so that's the omega due to the series part of the model, and here we have the omega p. This is again assuming that omega p is greater than omega s, which is what you want and is also required for the device to work. And the way that you cut physically, because it's really an electromechanical device, the way that you cut the device, the crystal or the ceramic, let's say along the lattice and the angle and things like that, it will give you the characteristics and the property. And what you want is that the parallel omega is greater than the series omega. So if we were to draw a line along this ways and plot the reactance of the crystal, it would look something like this, and then asymptotically approach omega p, and then beyond omega p it would look something like this. So essentially the reactance would be capacitive everywhere. So this is negative reactance, so that's capacitive here, and here it would be inductive. Okay, so there is a very narrow region between omega s and omega p where the reactance of the device is inductive. And by manipulating the physical properties, you can set omega s and omega p, and then set the where the device is going to offer that that oscillation. So if we were to concentrate on this model of the device, we can calculate the impedance of that combination of inductor, capacitors, and resistance. The other thing also is that normally the R is very small. So the R is very small, and usually the impedance, because the R is very small, the impedance can be approximated as a reactance, because you can approximate the R as 0. So in other words, R very small, and that implies that Z is almost X. Okay, but so let's look at that impedance then, which is the reactance. We're going to use this property. We're not going to take into account that resistance. Okay, so if we just using the Laplace impedances and combining the impedance individually, what we get is that the impedance of the model, if we ignore the resistance, is SCP plus 1 over SL plus 1 over SCCS and a 1 there. Okay, so we can manipulate that a little bit, and that would give us and this is a 1 over here as well, S squared plus CP plus CS divided by, sorry, L times CS and CP. So that's another way of writing that. If we solve for the series resonant frequency, what we find is that WS or omega S is equal to 1 over the square root of L times CS, and the parallel omega is 1 over the square root of L, and then the parallel the series combination of CS and CP. So these are the expressions for omega S and omega P, and I can go back to the impedance. I can go back to the impedance expression and get an expression in terms of omega. And that multiplies there. So in this case, CP, omega S, and omega P are constants. So this expression gives me the impedance in terms of omega. It gives that graph that that we saw. So this is the key result of that analysis. So that gives us something to work with, and it's just really good information because the crystal by default is set. So you cannot use a crystal for any frequency. Each crystal will have its own frequency that is optimized for, and you will use that to use it as a feedback or beta mechanism with an amplifier to make oscillators. So the most common oscillator is what you find in all kinds of digital chips and microcontrollers and things like that, which is a simple inverter. So an inverter can be seen as a very high gain amplifier. So it's a simple inverter, and maybe you have some a little bit of a resistance, loading resistance in the inverter, and then here you have your crystal. Now the crystal also works with a pair of capacitors to complete the circuit, and this is something that you get out of the data sheet of the crystal. So that would be, let's call this C1 and C2, and then the other thing that you have is a feedback resistor here. So this is all implemented inside a chip, and all you get two pins, and maybe some of you already work with that. You get two pins, and you put the crystal, the two capacitors, and you get yourself an oscillator, and that's called the Pierce oscillator. So probably the most widely used oscillator these days. Now, if we look at this configuration and the actual values and realistic values that you get for the capacitance models in the crystal, one thing that you see is that the series capacitance is much smaller normally than the parallel capacitance of the model, as well as the external capacitors of the Pierce oscillator. And if you go back to the analysis of the impedance that we did before, what that means is that the frequency of oscillator is given by one over the square root over LCS. So that's which is the series omega. Okay, which is the series omega, and that should make sense because if you look at the graph, that's the better defined part of that graph of reactance versus omega. So just to complete the part in oscillators, any questions at this point? All right, so now let's look at another type of circuit that fits well with what we're doing in this chapter. Those are called nonlinear oscillators, and also they could be called function generators. And a close cousin of this circuits that we're going to be looking at here is what you are looking for your project, the one-shot. So the one-shot is one type of bistable type of circuit. So you will recognize some of these things as you have been looking and researching the one-shot. So let's look at the bistable feedback loop. And what you have seen this, that part of that one shot is this type of op-amp configuration. Of course, that will put more things there, but one type of bistable feedback loop looks like this. So this will never be stable because you have a feedback going into the positive input of the op-amp, and it'll keep, in this case, it'll keep switching back and forth between the power supply rails of the op-amp. And if you were going to look at the transfer characteristic, what we would see is that let's look at let's just for the future call this R2 and this one R1. But if we had a transfer curve, so this is probably the best space to do that. If the input, in this case, the input being the differential input of the op-amp, so that the voltage here, okay, as we decrease that, and this voltage here, let's call it L plus, and of course it's going to be something close to the rail. No op-amp perfectly drives to the rail, but maybe a little bit lower. So this is VO, and this would be the input voltage as defined at this node. As we go through and start increasing, that is going to switch to the negative rail. So we call that L minus there. And then as you keep increasing that, it's just not going to change anymore. So Now the idea was that it was at this level to begin with, and we'll see what happened. So the transition and the trajectory of that voltage is like so. Like that. So we can call this voltage here, this is a transfer curve, so it's voltage versus voltage, voltage out versus voltage in, as defined. We can call that the threshold voltage for switching. Okay? And it doesn't matter how much we increase that, it's just going to stay at that L minus. Now, if we start decreasing L minus, decreasing that input voltage, what we'll see is that it's not going to switch at this point. It's going to keep going until the input voltage reaches a level that is negative at this point, and is going to switch. So this is the trajectory on the input becoming less and less. And this value here would be minus VTH of the threshold. So this is a bistable loop. So this is the bistable loop here. And what that gives us is hysteresis. So that's a classic hysteresis behavior. That this op amp with that feedback in the positive configuration has. So we can take advantage of that behavior by using it. And what we can do is use that as an amplifier and then set the timing with the beta network. So what we could do is now get rid of this ground point here, and we can set timing by using an RC network. So now this starts looking like your one shot a little bit, although this is different because this is an oscillator. The difference of the one shot is that it actually gets triggered with an event, and that's how you use the diode to actually trigger and discharge that capacitor based on an external event. Here we have no external event. This is an oscillator, but it's the same principle. It'll reset itself according to the timing set by this RC combination. So let's call this R and let's call that C. And what we will see at this output is this type of hysteresis loop. So we're going to see this at the output, where this is going to be L, and this is going to be L minus over here. And then at this point here, we're going to get basically, it's going to be an RC type delay waveform of that square wave. So it's going to be something like that kind of a thing, which is going to switch given the beta, this is our beta over here, so this over here is our beta, is going to switch between the minus VTH and VTH, the threshold voltage. So you can set the frequency. Nothing you can do about the output. The output is still going to switch between L plus and L minus, but what you can set is the timing of this, because you can set the charge and discharge time of that capacitor by just picking the value. So this is going to be minus beta L minus, and actually no minus, because the minus is already in L minus, and VTH is beta L plus over here. So now you have an oscillator, very simple oscillator based on a bistable loop. This is also used in integrated circuits because of its simplicity. Like I said, it doesn't require like a great op amp, because all it has to do is switch, and you can build that easily with like 9 transistors, and then it just requires 3 resistors and a capacitor. And if you don't want to use your microcontroller's crystal and use the built-in RC oscillator, that's what they have. That's what they have inside the chip. Okay, very inexpensive. So let's look a little bit more about the nature of this timing here. Okay, let's look at the nature of that
Dr.
time.
Hernandez?
Yes.
Are you going to go more into hysteresis?
More into the hysteresis?
Yeah, because that's like the beta component. But is there any significance to the value?
Yes, yes, because the way, so what we are, and this is what we're going to do next, is that you cannot control so much other than by changing the supply of the op amp, the values of L plus and L minus. Okay, you set that first, but you have a lot of control on the value of VTH and plus VTH and minus VTH, because they are given by the beta times the value of L that you set. And we're going to take a close look at that next. Does that answer your question?
Yeah. Thank you.
All right. So let's look at that, and just here we have a fresh screen. So restate the fact that VTH is beta L plus, and I'm going to, instead of minus VTH, I'm just going to change that name to VTL. That's the low threshold. Okay, so that's the one on the left side of the transfer characteristic curve, and that's going to be beta times L minus. So that gives us that square wave generator, and you saw how we were essentially integrating that square wave with the RC circuit. And to take a closer look at that, let's write the time equation for that waveform out of the RC. So that's going to be, it's a first order RC circuit, so it's going to be so from your very first ENG 212 circuit is going to be this expression. Okay, now the V sub minus infinity is just the value of the voltage, so the final value of the voltage that eventually is going to be reached. So that's when the capacitor is charging. So that is this timing equation is for the charging part. So that's for that part for the capacitor. So when it's charging, and that's what we're going to look at now, okay? So we can, I mean, this is the general expression, but first we're going to look at it when it's charging, because the values of V sub infinity and V sub 0 plus, they take different meanings whether you are charging or you are discharging. So when you are charging, the value that you are interested is V minus, which is going to be the eventual, so the V infinity, the eventual value of the charging voltage is going to be L plus, and then L plus here, and then the value that triggers it, which is V sub 0 plus, the value that you start from and triggers the switching is beta times L minus. Because if you're going to L plus, you were at L minus. And where do you start switching? Well, you start switching and start charging at this voltage. Okay? Now, of course, tau is just RC. And the voltage that you are going to, or no, not the voltage that you're going to, but the voltage V, small v minus, is your input voltage into the biastable loop, which is the output of the RC network. So that's going to give you the voltage when you start switching again. And that's going to happen sometime t, which we're going to call t1. So that's going to give you one phase of the output at the biastable loop. Okay? Now, let's use this expression again to look at the discharging part. When we're discharging, we are at beta L plus, or that's what's going to make us start discharging. So in that case, and we are at L plus, and beta L plus gets us to start discharging. So then, for discharging, our voltage, so this V minus is again the input voltage. The minus here means that it's at the negative input of the op amp. So that's at the top of the capacitor. So we are eventually going to reach, since we're discharging, we're going to reach L minus. So we're just applying the different values of the infinity and V0 plus to the general expression. We eventually are going to reach L minus, and what's going to get us to discharge is beta L plus, because we were at L plus. Okay, and then the voltage at the negative input of the op amp is beta L minus, because when we finish discharging, that voltage is going to become beta L minus because we are going to be at L minus. And that's going to happen at T equals T2, which is the discharge time. So now, if we take the frequency of oscillation to be T equals T1 plus T2, then we can solve for the frequency of oscillation. Okay, let's take for example T2, and the same can be said for T1. For T2, if we solve the discharging equation, which is here, if we solve this, for T2 by just putting T2 in place of T and beta L minus in place of V minus, what we'll get is that T2 is tau ln of 1 minus beta L plus over L minus and 1 minus beta. So, but that's just for T2. But we know that T, which is really what we want, which is the frequency of oscillation, is going to be T1 plus T2. Another simplification that we can make, and it's not a crazy assumption, it's a very valid and reasonable assumption, is that L plus is equal to minus L minus. So meaning that the oscillation is between the same voltages, just plus and minus, which are the power supplies of the op amp. And if you apply this and you take this into consideration and you take into consideration the same thing for T1, what you get is that the overall period, and therefore that would be 1 over the frequency of oscillation, is 2 tau ln of all right. So now I can set my frequency of oscillation. Any questions so far? Okay. And I guess to wrap it up, what we could do with this oscillator is we're going to what we could do with this oscillator is to come up with a triangular waveform generator. So if we have the same hysteresis loop, so this is that op amp that gives us the Same hysteresis deal here. If we have that, if we add instead of just an RC, if we add a Miller integrator here, so instead of just an RC, we have a Miller integrator. Then what we get out of here is a nice triangular waveform. Same behavior, okay? But then we get a triangular waveform, so which is a nice function to have. Here we still get the same square wave, okay? And so this is going to be L minus to L plus. This is going to be T1, T2 together is going to be D. So nothing has changed. What changes is really the properties of the of what you get at the input of the op-amp. So this is our V minus over here still, because we have that bistable loop in there. And what changes is the property of the waveform at the triangular output, and the slope of that slope here, the slope is going to be minus 1 over RC, and here the slope is going to be 1 over RC, the RC of the Miller integrator, okay? And actually that gets multiplied times L minus, okay? And L minus here, which is the same as L plus. So, and that this is going to be switching just like before at the beta times L minus and L plus values. So that's going to be your V, your VH, your threshold, or VTL, and this is going to be V threshold high. So let's take a closer look. So we said that this is T1 and this is T2. All right. So let's look at T1. Just looking at the graph, and from the graph computing the slope, VTH minus VTL, that's going to be L plus divided by RC, and at T2 that's going to be well, before that, let's just write that T1 just by looking at the graph is CR, and actually solving this for B1 for T1 is VTH minus VTL divided by L plus, And if we do the same thing for T2, from the graph we can write VTH minus VTL and if we solve for T2 we get CR times VTH minus VTL divided by minus L minus. And that gives us then the frequency of oscillation, which is 1 over T, which is equal to T1 plus T2. So here you have a circuit that gives you a square wave, it gives you a triangular wave, and then what you can do is add another op-amp based circuit, and you can filter the fundamental out of the say the triangular wave. You can filter the fundamental and then you get a sinusoid. So now with another pretty simple filter and 3 op-amps, you have a function generator for a square wave, triangular wave, and sine wave. And you can start, refining from that. You can make the value of the components adjustable, so you can change it and maybe amplify and change the levels, and also add some digital logic to dump the charge and maybe get sawtooth type waveforms, and all of a sudden you got a full-blown function generator like what you're used to using in your lab. Okay, so that concludes chapter 15